Okay, big surprise at the end of this video. We're going to unveil the secret to logarithms. So let's talk a little bit about logarithms. Oh, the secret to logs. Logs, you guys, are just inverses of exponentials. Okay, so I can write a logarithm in the form of an exponential. There's three pieces. There's a base, there's an exponent, and there's an argument. Okay, here's our base. Our base is 3. Here's our exponent. Our exponent is x. And here's our argument. Our argument in this case is 81. Okay, now, a couple of things. Your argument must always be greater than 0, and you'll see why in a couple of minutes. Okay? What do you remember about how that turns into an exponential, or do you have no idea? 3 to the x equals 81. Is that possible? Yeah, 3 times itself, how many times? 4 times. So x equals 4. Okay, let me take you to another friend of ours. This is called the common logarithm. The common logarithm, what's probably the most common number in our number set? Not 3. Most common number, 10, right? You got 10 fingers, 10 toes, hopefully. The common logarithm, base 10, if I told you that this was 2, what would you say the argument would be? 100, good. The common logarithm is typically written without writing a number. So you, at this point, should know that that would equal 2. Okay, because what's the base? Well, the base isn't there. If there's no base there, then we assume it's the common logarithm. Okay, so that'd be 2. Could you tell me what this would be? What would that be equal to? -1, right? -1, because 10, which is our base, to the -1 would be equal to 1/10. Are logarithms coming back to your brain a little bit? A little bit? Okay, let's pause for a second. What about the natural log? I'm going to write it cursive because I'm feeling like it. Natural log is base what? Base e. Now, we could write it like this, but this is too much work. Right? What would that be equal to? 1, right? Because e to the first power is e. But we will typically write this in this form. And the reason why I think a natural log was created by someone French is because I think L stands for log, and I think N stands for natural. Log natural. But that's just a theory. That's just a theory of mine. Croissant? Okay. Of natural log. Could you tell me what this would equal? No. No, it'd be 0. Why? Because Talia just used your calculator. But what would the base of this be? What would the exponent be? Base is e, exponent is what we're looking for, argument is 1. So e to what power equals 1? Yes. If you ever see that your argument is 1, you know your power or your exponent has to be 0. Yeah. That's good. Okay, so I'm going to prove number 1 and 3 to you in a couple of minutes. Number 2 will be kind of like number 1. But number 4, check this out. Let's say I don't know what this is equal to. Right? How would I write this in exponential form? A to the x equals b, right? Well, if I don't like working in base A, what I can do is I can take the common log of both sides. All right? And what I can do from there, and you're going to learn this in a minute when I prove it, but I can take this exponent and I can bring it down in front. And you'll see why in a moment. Oops, that should be a 10. And what could I do to solve for x? If I want to get x all alone, what would I divide by? Log base 10 of a, right? So if I divide by log base 10 of a, log base 10 of a, what I've got here is that cancels and I get x equals that thing. Oh, cool. Log base 10 of b over log base 10 of a. Why is that useful? Because log base 10 is so much easier to work with, right? 10 to whatever power equals a number, right? Makes sense, makes more sense. It'll make more sense even more later. How would I write this in exponential form? A to the what? 1, isn't that equal to a? Oh, yeah. A to the 1 equals a. A to the 0 equals what? 1. If you ever see a 1 in the argument, boom, we know that the exponent has to be 0. How about a to the x equals 0? Can I make a positive number to an exponent be 0? No, you can't. So there's no answer there. That's not possible. And then this one we'll talk about in a little while here. All right, here comes the proof. This is where it gets awesomeness. I'm going to prove to you that I can bring the exponent from the argument out in front. So I'm going to set log base a of b equal to x. So naturally, I can then show that a to the x equals b from that, right? I've got a to the x power equals b. Okay, so now I'm going to prove this using my awesome glasses and some math knowledge. I'm going to take both of these to the n power. Therefore, I would have a, what would I do with the x and the n right here? Multiply or add? Multiply or add? Multiply. So I'd have x times n, and that would equal b to the n. Now, something that you can always do, you can do an operation on both sides as long as the operation is the same. I'm going to take log base a of both sides. I don't really like how that's spaced, so I should probably move it over. B to the n. And I'm going to take log base a of that. All right, so now what can I do from here? Well, let's take this piece here. I want to examine that. What would log base 2 of 2 to the 5th be? 2 to what power gives me 2 to the 5th? 5. What would log base 3 of 3 to the 7th be? 7. So what would log base a of a to the xn be? Xn. I'm going to put it as n times x. Oh boy, here it comes. I bet you're excited. You're like, I can't wait. It's only 3 days till Monday when I can get to do more of this. Am I right? Yeah, okay. What did x equal above? Log base a of b. So n times log base a of b equals log base a of b to the n. So what can I now do? I can take this exponent that's from the argument and I can bring it out in front if I want. It's a nice little skill we have. Oh. Okay, so what I'm going to do is I'm going to prove that log base a of x times y equals log base a of x plus log base a of y. So addition means multiplication. Hold on a second. This is cool. You're telling me that multiplication means what? Addition. Oh, right? Logs are exponents. That's all they are. So check this out. This is a to the x equals b. This is a to the y equals c. Go figure. We're using products, so I'm going to multiply these together. So could I say that a to the x times a to the y would equal b times c? Anybody disagree? Don't, because it's right. Okay, so what do I do with the x and the y? I add them. And I am allowed to, at any point, take log base A of both sides as long as it's the same base. Oh, we're almost there. We're almost there. What can I do with an exponent now? What can I do with this thing? Bring it down in front. So I'm gonna. X plus y times log base A of A equals log base A of B times C. What would the log base A of A equal? 1. So X plus Y equals log base A of B times C. And what was X? Log base A of what? B plus log base A of C equals log base A of B times C. Oh, proof. QED. Awesome. Like, subscribe, comment below. Pion. Look at that. Proved. If you like this stuff, you're 1, a sick individual, and 2, you're going to love calculus. Here be some examples. Let's do a couple together. Okay, first of all, your argument, right, in logarithm form, the thing inside the parentheses can never be negative, right? It can't be negative. So this number right here, and this number, and this number, and this number, and this number, and this number. Oops, hold on. Not that one. And this number, none of those are called the argument. They can never be negative, ever, ever. Okay? So let's write a couple in log form. Okay, what's the base of this log? 5. What's the argument? 1 over 125. And our exponent is -3. This should be pretty straightforward, right? Are there any that look kind of yucky? Not really. This is just reforming what we did before, right? Sure, 15. What base is that? No, that's not 10. That's French, so it's e. So it's e to the -1/2 equals 1 over square root of e. Would that be true? Well, I hope so, because we put it on there. This would be 1 over e to the +1/2, which, yeah, that would be true. Right? That would work. Okay, let's get something a little more funkier. Yeah, oh, here we go. Evaluate. Now we got to evaluate. Let's look at 16. 3 to what power gives me 27? Third. Okay, that's 3. 6 to what power gives me 1/36? Well, 6 to the 2 gives me 36, but 6 to the -2 gives me 1 over 36. Okay, let's skip to something a little more challenging. Let's do one more in the left column. Yep, this would be 1/4. Oh, this one would be nice. This would be 2/16. That's easy. How about this one? Number 37. 5/3. 5/3. Yep, 5/3. Cube root to the 5th. Good. Okay, let's move over to the eastern side of the board and see if we can. Yeah. Actually, this is northern. That's north. East is behind you. 30 what? 39. How about 39? Let's do it. 39. Oh, yucky. Okay. I want to know what this is going to equal, right? So 5 to what power would equal 3 to the log base 3 of 5? Okay, this is a good problem. I like it. No, right? I'm just rewriting this. Nope, 5 would be, this is the base, this is the exponent, right? We'll get there. I know exactly what you're saying, but we'll get there. Let's look at this for a moment. Let's just see what this thing would equal. 3 to the log base 3 of 5. We want that to equal something. So how would I write that in logarithmic form? What's the base of the exponent? 3, right? That's our base. What is our exponent? Log base 3 of 5. What's our argument? It's x. Well, what does that tell me that x equals? 5. Sick. So this is really just 5 to what power gives me, this we said was just 5. So what would that be? That'd be 1. Yeah, we'd evaluate that to 1. Oh, sick. Check this out. This is a nice little shortcut you can do. If you ever have e to the natural log of 7, or 4 to the log base 4 of 7, or 9 to the log base 9 of 7, what are the answer to all those? 7. E to a log of base e, 4 to a log of base 4, 9 to a log of base 9 will always be whatever the argument is there. And that, I think, gets kids. Just, we'll get there. Okay, we'll get there. Should we do one more? Let's look at 21. How would I write that? 36 to the x equals 216. Oh, no. 36 squared is a lot bigger than 216, right? But I think I'm pretty sure that this is 6 cubed. You might not be. But I know 216 is 6 times 6 times 6. Is there a way I could write this as base 6? Wouldn't 36 be 6 to the 2? Right? So wouldn't I just be comparing 2x to equal 3? Yep. And therefore x would equal 3 halves. Oh, chow. Or chow. What's true about this thing? It could never be what? Negative. Could it ever be 0? No, it could never be 0 either. Remember, right? We did this. Log base 7 of 0 equal x. There's no way I could write something, have an exponent to make that equal 0. Therefore, this thing, the argument, has to be greater than 0. So my x values in this case, I'd have 4x is greater than negative 8. Therefore, x would have to be greater than negative 2. That would be our domain for that one. What would be our domain here? X has to be greater than what? How about 5? The argument has to be greater than 0, but that means x has to be greater than 5. Oh, and we thought polynomials were going away. Okay. So x squared plus 9x plus 18 has to be greater than 0. Oh, I'm going to factor x plus what? 6, x plus 3 greater than 0. Oh, should I test values or should I graph it? Should I graph it? Does this parabola open up or down? Up, positive leading coefficient. Okay, so I've got a negative 3 and a negative 6. And the parabola is going to open up. So is it okay if I say that from negative infinity to negative 6, and from negative 3 to infinity, that would be greater than 0? Yeah, that'd be the domain of that function. Grossness. Ew, yucky. Okay, that's enough.